in this lecture video, we're going to talk about how we can modify the electrical properties of silicon through impurity doping. So this is why silicon is used in microelectronic industry. The reason that we use silicon or we love silicon is that we can have a lot of control over how it responds electrically. And we see that we can do it in two different ways. You already know that we can have P and N type doping in silicon. In this lecture, we're going to see how those are done. So from the electrical conduction point of view, you divide materials into three different categories. You have insulators, where they do not basically show any electrical conduction or measurable electrical conduction. What these are is that you have a nucleus here. We are talking about pure materials here, but compounds and molecules are similar. But you have atoms here that are very tightly protecting the electrons that are around them, so they don't let the electrons to take away or to get away from the atom. You have a very strong bond between the atom and the electrons around it. Dielectrics, compound or atomic, molecule or atomic, you do not have free electrons. In quantum domain, it's easier to think about valence band and conduction band. So a valence band is where you have, if you have an electron there, it's not able to contribute to electrical conduction. For an electron to contribute to electrical conduction, it has to be in a conduction band. And there is a band gap that separates the top of the valence band. So this is a bunch of energies that your electrons may have. And conduction band, the red one in this figure, where contains the energy levels that your free electrons can have, or electrons that are loosely bonded to your nucleus or molecules or atoms may have. So for an electron to move away from where it is in that lattice, in that crystal, or even an amorphous material, it has to be in the conduction band. Okay? So with that definition, insulators are materials that have almost all of their electrons in valence band, and they cannot get to the conduction band because they need to jump over this band gap between the conduction and valence band, and that gap is large. At room temperatures, where you normally get your energy, the required energy to jump from the valence band to conduction band, you normally get it from temperature, thermal excitation, right? And the gap is, let's say, 3 electron volts, 4 electron volts, 5 electron volts. It's so large that normally there's a very small chance that an electron will have enough energy to jump from valence band to conduction band and then just move away. So those are insulators. On the other hand, you have conductors. And in conductors, one way of thinking about them is that these are, for example, atoms, metallic atoms, that they have 1 or 2 electrons that they don't really like that much. They are happy to let them go. The electrons are loosely bonded to those nucleus. And from the quantum mechanical point of view, you can think about it as an overlapping valence and conduction band. And either the conduction band overlaps the valence band so that the electrons can actually move between these two bands relatively easily, or the gap between the valence band and the conduction band is so small that at room temperature during normal operating temperatures, you have an almost infinite supply of electrons. And you have heard the term sea of electrons. You have a sea of electrons. They are actually a lot of electrons that can be moved away from where they belong in the crystal. If you drop the temperature to near 0, where you remove all the energy from these electrons, they will be closely bonded to their nucleus. But as soon as you raise the temperature, they basically are free to move. And then we have a third category of the materials that is somewhere in between. So there is a band gap between the valence band and the conduction band, but it's not that big like insulators. It's like on the order of 1 electron volt or so. And therefore, normally you do not have too many electrons in the conduction band. Normally all of your electrons are in the valence band, but you have enough that you can actually measure some electrical conduction if you apply, let's say, a voltage across a piece of these materials. So these are the interesting ones. So with the insulators, you basically have no electrical conductivity. With the conductors, you have excellent conductivity. But with the semiconductors, you are in the middle. You are somewhat a bad conductor or a bad insulator. But what we see here is that you can actually play with that conductivity a lot more than what you could do, for example, with an insulator. And with metals, you can almost do nothing other than cooling them down. So let's look at a silicon crystal. This is a 2D drawing. We already know it's a 3D structure. So this is highly simplified. And in this crystal, what I'm showing is that the silicon atom is from the fourth group in periodic table. So it has 4 electrons in its outermost shell. Therefore, and then we know that they want to have 8 electrons, or pretend to have 8 electrons in their outermost shell. So what they do is that inside the crystal, each silicon atom shares its 4 electrons with 4 neighbor silicon atoms. And by doing so, each one of them sees 8 electrons in their outermost shell. They're sharing 4 of their own with 4 neighbor atoms, but they see effectively 8 of them. They're sharing it. And it's a covalent bond between the silicon atoms in a crystal. And everything is tight and neat, right? So the electrons are happy where they are. Silicon is happy where it is. It's seeing 8 atoms in its outermost shell, and the electrons are fairly tightly bonded to these silicon atoms. From time to time, you may have enough thermal energy that you break one of these bonds and one of these electrons becomes free to move. It's not too hard to do so, but it's not that easy either, right? So this is where the semiconducting part comes about. Now, let's assume that we take one of those silicon atoms out, which is from the fourth group in periodic table, and put a phosphorus atom in there, which is from the 5th group in periodic table. Now, a phosphorus has 5 electrons in its outermost shell. It comes in this silicon lattice, and it sees 4 silicon atoms nearby. It shares 4 of its electrons with those 4 silicon atoms, and now it sees 8 electrons in its outermost shell. It is now happy. So it actually doesn't like the remaining electron that much. What that means is that if you have a tiny bit of thermal energy, if you introduce a tiny bit of thermal energy here, if you raise the temperature to, let's say, room temperature levels, it is happy to get rid of that extra electron. So phosphorus with 5 electrons in its shell comes in, is happy, it's making a covalent bond with 4 neighbor silicon atoms, and gets rid of one of its own electrons. So once the electron moves away, let's say because of an electric field that you apply across this structure, you have a phosphorus atom that is ionized. It is missing an electron, so it's a negative charge that is inside the lattice. It is fixed, and you have an electron that can actually now move about. So it can go from one corner of the lattice to another. And now if you apply an electric field across this structure, for every phosphorus atom that you have there, as long as it is ionized, as long as the temperature is around the room temperature, you get one conductor, one charge conductor, right? So one electron. So you expect it to be more conductive, or the lattice to become more electrically conductive. Phosphorus is called an N-type dopant of silicon. The reason for that is that it is adding a negative charge carrier to the crystal, to what we had before, right? And it's called a donor. It is donating a charge carrier to the crystal. Now, you could also go and take one of those silicon atoms out and put a boron atom in its place. In this case, boron is from the 3rd group in your periodic table. It has 3 atoms in its outermost shell. It needs 5 to see 8 atoms in its outermost shell and feel happy. So what happens is that once your boron goes into your silicon, it is just looking for an extra electron from wherever the possible What happens is that at some point, because of the thermal energy that you have in the environment, one of the bonds breaks in your crystal, your silicon, and your boron atoms grabs onto that electron and holds onto it. So what you have is now a boron atom that is negatively charged and a bond that is broken somewhere else in the crystal. A bond that used to be the place or location that used to be the place of an electron, but now your boron has grabbed onto that electron, is tightly holding to it. So your boron is now ionized. You have a negative boron ion here, and you have an empty spot for an electron. Now what can happen now is that the empty spot that you have inside this silicon crystal, when all of those bonds are more or less the same, a bond nearby can break and one electron can jump from one of those bonds into this empty spot. Right? So you get an empty spot for an electron somewhere else in the crystal, but this bond is now happy. It's as if you had a positive charge carrier, right? It's the empty spot for an electron. The electron moved here, it's as if the positive charge carrier moved over there. And then it can keep moving around the crystal. It's not a real charge carrier. We know it is the empty spot for an electron that is moving about. But it helps us in terms of writing equations and solving them to treat it as a positive charge carrier. We call it a hole. The reason for that naming is that it's actually the empty spot for an electron. There used to be an electron here. Another electron came and filled this spot, the spot for an empty electron, but we have an empty spot for an electron up there. So it's called a hole. It's called, it is treated as a charge carrier. It is a positive charge carrier. And you can see that, well, this thing shouldn't be able to move as fast as an electron. You know, for that hole to move about, you need some bond somewhere else to break so that the electron can move here. So when you do the calculations, these holes actually move a little bit slower than electrons. A free electron in the case shown before. In a lattice, it's as if they are heavier than an electron. So the effective mass of an electron is actually less than the effective mass of a hole. Now, because the charge carrier that we have here is a positive charge carrier, we call boron a p-type dopant. So in the first case, we had phosphorus, which when it ionized, you had a positive charge. I think I may have said a negative charge, but you have a positive ion there, and it donates an electron to the lattice. Notice that you still have charge neutrality, right? So the electron and the positive charge cancel each other when you integrate over the entire volume. In the second case, you have boron, which grabs onto one of the electrons from the lattice and becomes negatively charged itself. It is fixed in its place, but the empty spot for the electron can move about. We call that a hole. Now, same thing as what we had for the donors. We call it an acceptor here. The boron, we call it an acceptor dopant here because it is accepting one electron from the lattice. It is a positive charge carrier that it donates, so it is a p-type. But again, you can see that for every boron atom that is ionized, you get one charge carrier in the network. So for every boron atom, you get more charge carriers. If you increase the number of boron atoms, you will have more holes. So therefore, better conductivity, electrical conductivity. Same thing with n-type dopants. If you increase the number of phosphorus atoms, you get more electrons. However, you can see that these two are working in opposite directions, right? So an electron is donating an electron, an n-type dopant is donating an electron, a p-type dopant is accepting an electron. So if you add both of them, some will cancel each other. But when added on their own, each one of them is actually improving the electrical conductivity. So if you look at how the conductivity changes with the dopant concentration, this is a graph. You can see that for p-type dopants, you get slightly higher resistivity than n-type dopants for the same concentration. And the reason is that issue that I mentioned, that holes move a little bit slower than electrons in a lattice, in a silicon lattice. And therefore, you get a little bit higher resistivity for the same number of dopants. But nonetheless, you can reduce the resistivity by increasing the number of dopants. Our typical doping levels are between 10 to the 16 to 10 to the 19. This is the sweet spot, is about 10 to the 17 to 18. This is where we make most of our p-n junctions. If you want to get highly conductive regions, you dope them to 10 to the 19 or higher. And if you want areas that are almost insulating, you make sure that the doping level in those areas is below 10 to the 15 or 16 if you can manage it. And then only remember that for silicon you have about 5 times 10 to the 22 atoms per cubic centimeter. So even if you dope at the level of 10 to the, let's say, 18 atoms per cubic centimeter, that's the unit we normally use, if the number of dopants is that many, it still means that it's roughly 1 out of 50,000 silicon atoms that you've replaced with a dopant atom. It's a tiny fraction of the total number of silicon atoms that are there. You're talking about 1 in 1,000 to maybe 1 in a million. Now the question is, how can we do that? How can we just add 1 part in a million of phosphorus to a silicon crystal in order to get the resistivity that we want? And then for the sake of comparison, remember that the electrical resistivity for aluminum, for example, is about 2 microohms centimeter. For silicon, you don't really get to that level, even if you dope it to about 10 to the 20 atoms per dopants per cubic centimeter, right? So you're still far from metals, but you're getting close. So how can we dope a substrate? How can we replace 1 silicon atom out of a million or out of 100,000 with the dopant atom that we want to? There are 2 different ways of doing it. What we can do is, actually 3 different ways. What we can do is that when you make the wafer, just add the right amount of dopants to your melt, and hopefully they will end up in your wafer as designed. But you don't have that much control over there, because we saw that the dopants tend to stay in the melt, so you get non-uniform doping across the ingot as you produce it. And also the issue is that, okay, so you have such and such doping on your wafer. Now what? You want to modify that doping. You don't want to just have a constant level of doping across the wafer. So this we do, and we call it background doping, but what is more useful to us is selective doping, that we change the doping at certain locations on the wafer as we need. So what we can do is that we can bring dopants close to the surface. Let's say in this case, what we have is, let me see if I can. So in this case, what we do is that we cover portions of the wafer that we don't want to be doped with some masking material, it could be a dielectric, and bring dopants close to the surface and let them get into the material, let them slowly diffuse into the substrate, right? And then as you expect, because you have the highest concentration of dopants at this opening at the top of this substrate, you have higher concentration of dopants here, and the concentration drops as you go deeper and deeper into the substrate. So if you look at the concentration, you have the maximum at the surface and drops as it goes, as you go deeper. So this is called doping by diffusion. You bring dopants close to the surface and you let them diffuse into the substrate. You can do it in a gas phase as shown to the left here, or in a solid phase. So you deposit a film that has a lot of phosphorus in it, and then you let the phosphorus in the film to diffuse into the silicon layer underneath. You can also do something different. You can go and take a phosphorus atom and just shoot it towards the substrate. And you shoot it at a high enough energy so that it goes and penetrates the substrate, right? So this is called implantation. You're implanting these phosphorus atoms into the substrate. Well, you cannot shoot atoms. It's not easy to shoot atoms. What we do is that we ionize them and then accelerate them in an electrical field and then aim them at regions that we want to dope. Because these are high energy atoms, they do not really stop, or ions, they do not stop at the surface. Usually they go a little bit below the surface and stop there, right? So you will have a concentration that looks like this if I go from the surface into the substrate. The concentration maximum happens at a distance below the surface, but then it drops quickly as I go deeper and deeper into the substrate. So let's look at these three methods. Well, the two different methods, the diffusion and implantation. But we see for diffusion, we have two options, so we'll talk about that. Now, the challenge is that if you bring a lot of phosphorus and just expose it to silicon, they do not really go into silicon, right? So the diffusion of phosphorus, if you just keep it above silicon here, is really, really slow. It's negligible. You really cannot get any phosphorus into silicon no matter how long you wait. What we'll do is that we raise the temperature, we increase the energy in the environment, we make the phosphorus atoms more energetic, and by raising the temperature, we make it easier for phosphorus to diffuse into silicon. So, as you can see here is, let me show you the equation. So the basic diffusion equation is as shown here. It says the flux of the material is proportional to the derivative of the concentration times your diffusion constant, okay? So how much of the material goes into, let's say, phosphorus or boron that you have at the surface, how much of it goes into silicon and move forward, is proportional to the concentration of these, and definitely the flow is from high concentration to low concentration, so that's the reason for the negative sign in that equation. And D is your diffusion constant. And the problem is that at room temperature or low temperatures, the diffusion constant is really small, but that's a temperature dependent coefficient. We raise the temperature and everything becomes easier. The diffusion becomes easier. On the right graph, you see how the diffusion constant changes with temperature. So the axis, if you look at the bottom axis, it's 1000 over T in Kelvin. At the top, you have it in Celsius. You can see that as we raise the temperature, the diffusion constant exponentially increases. You can actually find the diffusion constant from that equation, and the numbers for boron, phosphorus, and arsenic, that are your typical dopants, are mentioned in the table below. Now, we also look at the continuity equation. It says that the change in concentration of a material at a location is going to depend on the flux of the material that you take away from it, and the changes in that flux relative to location. And combining the continuity equation in your basic diffusion equations, you get the Fick's law, which says the changes in C with time are proportional to the second derivative of C. C is the concentration with length. It's a 1D problem we are considering right now, okay? And diffusion constant determines how fast that happens. Now, we have a partial differential equation that we can solve under different conditions. You are not required to solve this equation, so don't be, let's say, scared of what we have here in front of us. What we are going to look at is two special cases where we actually utilize this equation to do our diffusion, to do our doping. In the first situation, let's assume that we have a constant surface concentration of dopants, meaning that, let's say, you have your wafer inside a furnace, the temperature is high enough, 900 degrees, 1000 degrees Celsius, and I bring a flow of phosphorus atoms constantly to this surface. I make sure that there is an infinite supply of phosphorus that is coming in and keeping the concentration of phosphorus at the surface of silicon constant. So under these conditions, these assumptions, well, the concentration at the beginning of the process is 0. There is really nothing that is inside my silicon substrate at the beginning. So C of x at t, at any x is the distance from the substrate, and t equals 0 is 0. And then as the process goes on, C of x 0, meaning the surface, at any time is constant. I keep it at Cs, some fixed concentration. So the surface concentration is constant. And the other point I Well, it's a partial differential equation, and it was a second derivative with respect to x, first derivative with respect to t, so I need one other boundary condition. The other boundary condition is that if I go very, very deep into the substrate, infinitely deep, I expect the concentration to be zero. I don't expect any of the dopants that I'm adding here at the surface to penetrate that deep, no matter how much I wait. If I go far enough, the concentration will be zero. So these are the three, well, the initial condition and the two boundary conditions that I have. If I go and solve the equation that I had, the fixed equation that I had, I get this solution. So you can show that the concentration of dopants as a function of x and t is given by that equation. Cs is the surface concentration, is what I used to keep constant at the surface by flowing, let's say, enough phosphorus or boron atoms at the surface. ERFC is the complementary error function. It's tabulated. It's a well-known function in math. And x over 2 square root dt is basically telling you the dependence of the dopant concentration on x and t. Square root dt is called the diffusion, the characteristic diffusion length, and x is the distance from the surface. So if you do the doping for 1 hour, t is in seconds actually, and at a given temperature, you can calculate d, the amount of dopant, the time of doping. You can calculate dt, the characteristic diffusion length, and you can figure out the concentration of your dopants at any depth from the surface. So you see the profile as shown here, the concentration normalized to Cs. At the surface you have 1, and it just keeps dropping as you go deeper and deeper into the substrate. And obviously the longer you wait, the more dopants you will have in the substrate. So what is going to happen is that because you're providing an infinite number of dopants, the longer you wait for your dopant, you get more and more of these dopants into the substrate. And if you look at the areal density, meaning that if you take 1 square area here and integrate all of the dopants that you have here from the surface all the way to infinite depth, that number keeps increasing, right? And it is called the density, the areal density of dopants. So basically I look at C of x and t. C of x and t, remember, was atoms per centimeter cubed. I integrate it over a given area or normalized area from the surface x0 to x infinity, and I expect that number to increase with time, right? Because I keep bringing in new dopants that are slowly diffuse into the substrate. So the areal density of dopants can be found from this expression. Again, depending on the time and temperature, temperature determines d, time is your characteristic diffusion length, you get increasing numbers of dopants into your substrate. So let's look at an example here. We are doing a boron diffusion at 1000 degrees Celsius, and the surface concentration is maintained at 10 to the 19. So let me just write down these numbers here. So okay, and we do this for 1 hour. The question is 3 parts. What is the characteristic diffusion length? Second part, what is the total number of dopants per centimeter cubed? Squared. So A is so what is the characteristic diffusion length? What is the total of number of dopants per centimeter squared, right? So if the areal density basically. And then last question is that at what depth does the concentration drop to 10 to the 15 atoms per cubic centimeter, right? So let's say if that's the background concentration of my wafer, I want to know how deep I should go into this wafer before my doping goes back to background concentration from p-type that I'm doping it. Okay, so let's solve that. I'm going to switch to my tablet here, and so part A is easy, and I basically have a shorthand here. What is d square root dt? What is q? And what is c? When does c become 10 to the 15 per centimeter cubed? So for part A, what we need is we need to calculate square root dt. So square root dt is equal to, the time is 3600 seconds. Remember, the time is in seconds. But d, I need to figure it out for boron. So what I do is that I go back to the graph that I have here on this slide 63. And for boron at 1000 degrees Celsius, I look at this graph and I read it off this table. Or I use the equation that I have here. Right? So you have the equation for calculating D based on D naught and EA and temperature. Just remember, temperature in that equation is Kelvin, so you need to go and convert 1000 degrees Celsius to Kelvin. But you can calculate it from that equation as well. So for boron, I have the numbers, plug it in here at that given temperature. I can go and calculate the given value for D. But if you read it off the curve, you should get more or less the same value. It's going to be 1.4 times 10 to the 14, 10 to the minus 14 centimeters squared per second. The first one is in second. Multiply these by each other, and you get 7.4 times 10 to the minus 6 centimeters. The unit here is in centimeters. Yeah, it's a bit inconvenient, but it is again historical, right? In the early days of microelectronics, when they were developing all those tables and formulas and all that, it was done in centimeters. Actually, it was inches in the US, but they thankfully switched to centimeters. And a lot of the tables that were developed or created back then are in centimeters. So we stick to centimeters, but you can convert it to micrometers or nanometers or meters if you want to. But just make sure that you pay attention to the units when you read them off a table or somewhere. Now, the second question is that what is the total number of dopants per centimeter squared? So again, we go back to the formulas that we had, and we have this CS, I need to read it off here, 2 square root dt over square root pi. And then if you plug in the values in here, you have all the numbers you need. CS was 10 to the 19 atoms per centimeter cubed, and the square root dt we just calculated, we'll get this value. So this is 8.4 times 10 to the 13 atoms per centimeter squared. What does that mean? It means that if I look down onto this substrate after my doping is done, after 1 hour of doping, and calculate all of the dopants that I see here and normalize it by the area, that will be the number of atoms. All of those dopants, if I assume they are at the surface, that's how many atoms I have. So I can actually calculate how many atoms I have inside the substrate if I want to. And the last part says, how deep should we go before the dopant concentration drops to 10 to the 15. Okay. So what I need to do now is that I have the equation for C of x and t, which is the one based on the error function. So 2 square root dt complementary error function of Okay, so let me just go back one step. I can see you have this equation. So C of x and t is CS, the surface concentration, and times the complementary error function of x over square root 2 square root dt, right? Now the question here is that at what depth does this drop to, let's say 10 to the 15? And what I do here is that so this value, I don't know x, let's just call it xj. I don't know xj, right? But I have that c, it is 10 to the 15. And t is fixed, the doping is done, I'm looking at it after the doping is completed. So what I need to figure out is that the xj is found from this expression. So xj is 2 square root dt of the inverse of the complementary error function of whatever you had here divided by c, right? So c of, let's just call it xj and t divided by cs. Okay, so this I already have the characteristic diffusion length, so this is 2 times 7.4 times 10 to the minus 6 in centimeters, I keep that in mind, times the inverse of complementary error function of, at that depth the concentration has dropped to 10 to the 15 atoms per centimeter cubed. My surface concentration was 10 to the 19 atoms per cubed. So this is 1 over 10,000, and the value for error function, a complementary error function, is tabulated. So you can, I will provide you with one for the quiz or assignments, but a lot of calculators nowadays can calculate that as well for you. So you go and look it up. What is the inverse of the complementary error function of 1 over 10,000? And that is going to be 2.75. So plug that in here, and you can show that xj is going to be, let me see, (41 times 10 to the minus 6 centimeters), or if you want to convert it to micrometers, it's 0.41 micrometers, or 410 nanometers. So it happens just half a micron, about half a micron below surface. You can see that you go from 10 to the 19 to 10 to the 15 is just 0.4 microns. Okay, so moving on, let's look at another possibility. In this case, I'm going to have atoms, dopant atoms, brought to the surface, a certain number of them, and then I provide the situation, the environment for them to diffuse into the substrate. So in this case, I'm not providing an infinite supply of the atoms. I have a certain number. So let's say I deposit a film that has this many atoms of phosphorus in it, right? So I deposit this film on top of my silicon atom, and then I just raise the temperature so that those phosphorus atoms can penetrate and diffuse into silicon. So in this case, I have a new set of boundary conditions and initial condition. Initial condition is the same. The concentration at infinity goes to 0, so this is the same as before. But the other boundary condition we have is that, well, if you count the number of dopants as they go into the silicon, it is constant. You're not bringing in new ones. So that's a fixed number. Whatever you put in at the beginning, when you integrate C of x and t over the entire depth, it should remain constant. You're not bringing new ones. You're just redistributing them. If you go through that and solve the equation, you will find out that the concentration is given by this expression. It's more like a Gaussian. And at the end of the story, the areal density is given by this expression. So whatever CS, whatever Q you have at the beginning, it's going to be CS times square root of pi dt. Okay. Now, Unlike the previous situation where we had a constant surface density that decreased as we went further into the substrate, in this case your surface density at the top will also change, right? So if you wait, you're moving the material from here, you're moving the dopants from here, and you're redistributing them into the rest of the substrate. So your surface concentration will start to drop as you do the diffusion over longer and longer times. But essentially, it's still a diffusion process. Because of a different boundary condition, you get slightly different profiling. They look actually very much the same, but in terms of what happens in the end, you're redistributing a certain number of dopants. In this case, constant total number of dopants. In the other case, you have an infinite supply of them. You can just dope as deep as you want to at any level that you want in the first situation. So let's look at an example again here for this type of a doping. So the assumption here is, let's say you're doping boron in this case at 1000 degrees Celsius, and the total number of boron dopants is kept constant at 10 to the 16 atoms per cubic centimeter. So 10 is square centimeter. Now the question is that if we dope at 1000 degrees Celsius for 30 minutes, okay, where do we form a junction? So assuming that the substrate is N-type, you're adding a P-type P-type dopant, you're diffusing using a P-type dopant. The question is that where do we get the junction? Where does the concentration of boron atoms become equal to the concentration of background doping? And what you can do here is, let me switch to my tablet again. So I go back to here, I can see that C of X and T is equal to Cs e to the minus x squared to 4 dt, and the areal density is Cs square root of pi dt. Okay, so these are the equations that I have, and I calculate dt first, the characteristic diffusion length. So part 1, square root dt, I calculated. It's the same as the previous problem, so it's it is half an hour. The previous case it was 1 hour. So we go and calculate it again. You read D for boron off the chart, or calculate it knowing the temperature, and using 1800 seconds for time, you can show that. So let's say this time we read it off the chart, and you do not get that accurate value. So previously we had 1.4 times 10 to the minus 14, I think. If you read it off the chart, it's really not easy to get that 0.4 part, but it's roughly 10 to the minus 14. And then this gives you 5.26 times 10 to the minus 6 centimeter as your characteristic diffusion length. Once you know that, you can solve to find the junction depth. So the second step is to see where C of X and X junction is equal to 10 to the 15. So I put it in the equation I have over there. I don't know CS. In this case, notice that I don't know CS, but I know the areal density, right? The constant dopant concentration of 10 to the 16, right? So I know Q. So what I do is that I plug that in here. So Q 10 to the 15 for the junction depth is equal to, for CS I put Q over square root pi dt. So Q over square root pi dt e to the minus xj squared over 4 dt. And because I know dt, I can solve it. I know dt and I know q, I can solve it. if I do that, you can show that xj is 392 times 10 to the minus 6 centimeters. Okay? So, and then you can convert it to other units if you want. So, an alternative method to doping, which one do we use more often? We actually use the first method more often, right? Because with this method, the total number of dopants is constant. You cannot really get too deep, and you cannot get to very high levels of doping. The longer you do the doping, the smaller is going to be the number of dopants at any given depth, because they just go further and further into the substrate. With the first one, it's easy. We just have a flow of gas of the dopants, and they keep bringing new dopants to the surface. And then with that method, we can get any doping level at any depth, theoretically. In most cases, we really do not go beyond maybe a micrometer in depth for doping levels on the order of 10 to the 15, 16. Now, with those two techniques mentioned, they have their own limitations, right? So I do not get any doping level that I want that easily. I have to pay a price in terms of temperature or doping time. And my profiles are always the ones that was shown. It just drops quickly from the surface. With implantation, I have more control. So in this technique, the third one that we mentioned, you ionize dopant atoms and you shoot them towards the substrate. You can do that at different densities of the ions, and you can do that at different energies of the ions. And with those two, you can get whatever doping level you want at whatever depth you want, in theory, right? Now, because you're shooting these dopants into substrate, it's an atom nonetheless. It's not really going to penetrate that deep. It's going to go, let's say 100 nanometers, 200 nanometers, or let's say a micron or two, and then they stop. They are stopped by the crystal that you're shooting them towards. They don't have that much energy to go, let's say, through the substrate. But nonetheless, if you manage the time, the dosage, and the energy of these ions, you have a lot of control over the profile that you want to get and the concentration that you want to get. The concentration profile is like a Gaussian, that the peak is below the surface. Remember, we need to slow down these ions that are coming in. So they go in, and then you have a maximum concentration somewhere below the surface. The higher the energy, the deeper that peak will be, the farther away from the surface that peak will be. And now the challenge here is that because, so this is going to be the equation. So it's like a Gaussian, right? RP is the distance of the peak of concentration from the surface, and delta RP is how wide that is. And I'm going to tell you what determines how wide that peak of distribution is. Now, and Cp is the concentration that comes from the energy that you use, the dosage, and the time. The dosage of the ions that you use to bombard the surface, and how much time do you wait. If you want double the concentration, wait twice as long. It's that easy. Now the challenge here is that you are bombarding a nice clean crystal with these high energy ions. They're going to create micro cracks into your crystal. And because of that, you will have a damaged structure at the end of implantation. Now, not only that, there is also a little bit of randomness to this whole process. Some of these ions may find a channel through your substrate. If you're looking at the 100 phase, for example, there are just openings. There are like these tubes that if a dopant just happens to be in the middle of that tube, they can go really, really deep into your substrate. So you lose some control over where you want to stop these ions. So you have a cracked structure, which actually helps you with that issue. After a while, you lose that nice little openings if you keep bombarding the surface of the crystal with these ions. But the other thing you can do is that you can just go and tilt the substrate a little bit. So if you tilt it, your 100 wafer, you all of a sudden lose those long channels that you had deep into the substrate. It looks a lot more crowded, and your ion will go and stop relatively close to the surface where you want it. But So this is one way of doing it. The other issue, the other way of doing it is to have a thin layer of, let's say, silicon dioxide on your surface. So you put, let's say, 50 nanometers of silicon dioxide. Your atom comes down with a lot of energy. They go through the silicon dioxide layer first, but silicon dioxide is amorphous. So they get a little bit of randomness into their direction. And they don't go that deep into your silicon anymore. They have, instead of going straight down, they now come with a somewhat of a, let's say, angle to them when they go through that silicon layer, the silicon dioxide layer, and that gives you more control over the depth. Now, the issue of damage to the crystal is still there. So you have damaged your crystal, and then what you normally do after an implantation step is annealing. So what you do is that you raise the temperature so that the crystal has a chance to fix itself, to anneal itself, to heal itself. And after that you have perfect crystal, but the side effect of that temperature rise is that some of your dopants will diffuse sideways, right? So these dopants are already inside your crystal. You raise the temperature to 1000 degrees, they start to move about. So you get a little bit of diffusion happening during the annealing step, but that normally is done very quickly, let's say 10 minutes or 1 minute or whatever that you need to fix to heal the crystal, and you stop it relatively quickly. In terms of the final profile, with diffusion, if you have an opening, the dopants will go sideways as well as downwards. So you get a little bit of doping beyond the edges of your opening. Ion implantation lets you just go down straight. Yes, you will have a little bit of diffusion during the annealing step, but that can be minimal. And therefore, you have more control over the profile of your doped regions. And therefore, in microelectronics, almost exclusively nowadays, we use implantation whenever you want to have control over diffusion, doping and doped regions.